Dear friends, we are continuing our discussion on short period mode, and you know what exactly we are talking now is about approximation. Why we are doing this? We want to get a simplified equation, so that some numbers, some parameters we can identify, which will help us in analyzing the dynamic stability of an airplane. In the short period approximation, this is important, this is the approximation, because you know that the exact is here, this is exact. Okay. You have to find the roots of this equation, and generally for business type aircraft, conventional aircraft, you will find that it has two complex pair of complex conjugates, and in one complex conjugate pair we find that the real part is largely negative compared to the other conjugate pair, and we try to understand the physics behind it. And we know now that the airplane in longitudinal mode can get excited primarily in short period, like it just oscillates like this and come back to the equilibrium in a very short time. And what is the assumption? During this short time, total velocity remain constant. That means the perturbed u is 0. So, one approximation is perturbed u is 0, right? And this understanding will help us in making this matrix in a reduced order form. What we did was, since the perturbed u is 0, that means this equation x minus xu, this into u, this into this into this, equal to x delta E, that is a superfluous equation, because there is no change. So, we are dropping this equation, right. Second thing we realize, since u of s, this perturbed u is 0, so this multiplied by this becomes 0, this multiplied by this becomes 0. So, we also delete this. Okay, clear? See, this into this into this makes no sense. So, we also delete this part of the matrix. And finally, we have a 2 by 2 matrix of this form, but be careful, we have assumed z alpha dot zq theta 1, that is airplane at theta pitch angle is 0, and we have also put mt alpha equal to 0, but generally you can understand that mt alpha is not 0, but no problem. We know here m alpha and mt alpha. So, this mt alpha, the value if you know, you can be clubbed into m alpha. So, for us interpretation could be m alpha has both the component because of aerodynamic moment as well as because of moment due to thrust, as a function of alpha or as a variant of alpha. In a sense, how does it change with alpha? So, this becomes a very, very simple matrix to handle, and from there we found out what is the omega n short period through which we got through the approximation, the damping ratio through this approximation we got, then we compared with the exact solution, and we found for this airplane values are fairly close, and we say generally short period approximation is a good approximation. Now, coming back to the other mode in which the airplane generally get excited in longitudinal plane is, one is short period like this, another is it can go like this and then damp out. It is a long period, and that is called Phugoid mode. So, we will be now talking about Phugoid mode. So, let me erase this out. So, we are talking about long period mode or Phugoid. Again, the key word is approximation. In the long period mode, is something like this. It gets excited like this and then come back to equilibrium. It is not a very good, but okay approximation if we assume the alpha remain constant That means perturbed alpha is 0. It's not a good approximation for your information, but okay, it's a classical approach, and you will see that this also will give us some very relevant insight to understand the longitudinal dynamics of an airplane, right? So, the moment I talk about perturbed alpha is 0, this is perturbed, right? Or I say alpha total is constant, and that is why when I draw it like this, although very approximate, I draw it like this, as if the airplane is going like this. So, there is no change in angle of attack. I repeat, this is not a very good approximation, but okay. So, if I assume that alpha perturbed is 0 because alpha total is constant, then we can again see how best we can simplify this matrix, and that is exactly what we will be doing now. Let us watch out. So, let me first write this matrix, then I will explain. This is S minus XU minus XTU, then G, and minus X alpha or minus ZU, and minus U1S, and here it is U of S by delta E of S, and here theta of S by delta E of S. This is equal to X delta E, and this is Z delta E. And you could see that I can always assume ZQ identical to theta 1 equal to 0. I will put another condition also. Let us see how we have got this. Since alpha perturbed, this is alpha perturbed, this is 0. So, I have got this one, this into alpha, second, when I do this into alpha, again it will come, this into alpha, this will also come, right. So, then this column, this one I will delete. Do you see what I am saying? If I open this matrix, this will be this term into this term, plus this term into this term, plus this term into this term, right. Now, since alpha perturbed is 0, so x alpha into alpha is SU minus Z alpha dot minus Z alpha into alpha of S, this one into theta of this one into alpha of S. Again I repeat, x alpha into alpha of S, S U1 minus Z alpha dot minus Z alpha into alpha of S, then again M alpha dot into S plus M alpha into alpha of S. This will vanish. So, I am dropping this. Also, understand this third equation, this is related to moment coming about the y axis, M alpha, right. But here you are assuming the airplane is going like this. So, this oscillation is not that dominating, right. Moment about the y axis is not that dominating, because it is going like this. Okay. So, as a first approximation, I am also saying this man is out. It is also apparently superfluous. Right. So, then I am left with this goes, this goes. So, what I am left with? I am left with this term, this term, this term, and this term. Right? That is exactly you find here S minus XU minus XTU, and for G cos theta 1, we are assuming theta 1 equal to 0. So, this is G is here, and for here minus ZU is here, and if you see here ZQ we have assumed to be 0, theta 1 is 0, so only minus U1S, and that is exactly here. Right? Let me repeat again. When I am talking about phugoid, what I am assuming? I am assuming if this is the phugoid, airplane is actually through approximation, right? It may not be very accurate. It's going like so. At each point, alpha remaining constant, or the perturbed alpha is 0. The consequence of that, when I multiply these two matrices, the second term x alpha will be multiplied by alpha of s. Here the second term, this one multiplied by alpha of s. Here the second term, this multiplied with alpha of s. Right? All will vanish because perturbed alpha is 0. Second thing, the third equation, which was here through m delta E, this is basically representing the pitching moment about the y-axis of the airplane. So, this sort of a motion we are talking about, but actually we are approximating the Phugoid mode. It is not, this oscillation is not dominating, this is dominating, right. So, not much of this oscillation, not much of moment about y-axis. So, we are saying this is also superfluous. So, we are deleting that. Okay. This is an approximation. Right. By doing this and putting additional conditions zq equal to theta 1 and equal to 0, we get this simplified version. Also, we can do one thing in practice, x delta E, we can assume it is also negligible. So, x delta E equal to 0. So, I put it here 0. Please understand those approximations what we are doing. Okay. Now let us handle this 2 by 2 matrix, and I can write u of s by delta E of s by using Cramer rule. This as z delta E into g divided by u1 s square minus x us minus zu by u1 into g. Similarly, theta of s by delta E of s is given as z delta E into s minus xu divided by minus u1 s square minus xu s minus zu by u1 g. Please note here, there is x2 is sitting here, and now I am writing only xu here. So, you can interpret this xu, if you are taking thrust into account, this xu is nothing but xu because of aerodynamic plus xtu. That means the thrust effect is been absorbed in xu. That is why I was telling you, if you know how to handle the aerodynamic part, then thrust part gets added. So, it's nothing extra you do. Okay. So, that should be very, very clear to your mind. Now, if I see this, what do you call this u of s by delta u of s or theta of s by delta u of s? These are called transfer function. That is, if I draw a block diagram, I will say I am giving input delta E of s, I am getting output u of s. What is this u? U is the perturbed u, right? Do not lose the inside. This is perturbed u. So, ideally it should be small u, right? And what sits inside this box is this transfer function. Okay? Transfer function. That is, if I want to know what is u of s, once I know the transfer function, this, which is primarily decided by the aerodynamic dimensional derivatives, right, and the flight condition, if I know this transfer function, I have to simply multiply by delta E of s to get u of s in frequency domain, and there are numerical techniques to convert from frequency domain to time domain. So, we say inverse Fourier transform. Right? Fine. Once we understand this, what is our aim? Our aim is to ask a question whether the Phugoid mode is dynamically stable or not. So, how do I check? I again follow the approach which we followed for short period approximation. Our aim is to find to answer a question whether the Phugoid mode is dynamically stable or not. And we know the characteristic equation is x square minus xu s minus zu by u1 into g equal to 0. And remember, the beauty of initially understanding second order system. So again, this is a second order system, and we know standard notation for second order system using natural frequency and damping ratio. So I compare these two and find out omega n Phugoid, P for Phugoid, as minus Zu by U1 into G. Right? Similarly, because this is omega n square, this is equal to this. Similar 2 zeta omega n is minus xu. So zeta p, I find it as minus xu by 2 omega Phugoid. As simple as that. Omega n will be under root of this, and 2 zeta omega n equal to minus xu. So from there I find the expression for natural frequency Phugoid and damping ratio Phugoid. Okay? And if I want to calculate for an airplane, I know Zu, I know the expression of Zu, I know the expression of xu. I can easily find out natural frequency, I can easily find out damping ratio. Right? Okay. If we do this for the example airplane which we are doing, then this value will come, omega n Phugoid will come around 0.082 radian per second, and zeta p will come as 0.046 or 0.046. But if you recall, the exact values were earlier computed by solving AS4 plus BSQ plus CS square plus DS plus E equal to 0. Those values were, this was 0.091 and this was 0.076 or 0.076, 0.91. Now you could see natural frequency estimation through approximate method. This is approximate for Phugoid approximation. This is okay, this is a bit close, but as far as damping ratio is concerned, this is not really the value which we would have liked. And that's why from the beginning I am telling you that Phugoid approximation is not a very, very good approximation, but still it has got some additional features which we must know, which will help us to design an aircraft or analyze an aircraft dynamics. Okay? So with that understanding, now we'll do a little bit of, we'll play around these two expressions and see what are the best information we can get out of these expressions. Let us take omega np. Omega np Phugoid is under root minus Zu g by u1. You know the expression of Zu, so I can substitute that expression here. So we will get, it is something like this, g by u1 to q1 s clu plus 2cl1 divided by mu1. What I have done, g by u1 is this one, and this is the expression of Zu, where there was a minus sign, so minus can become plus. So I get an expression like this. Okay. Now I do further approximation. I say CLU is negligible. You remember what is CLU? CLU was m into dCl by dm. Right? Especially for low speed, this value is very, very small or 0, up to 0.6 or 0.7 Mach number. So we are assuming that this value is 0. Then what we have is omega n Phugoid equal to, so this man goes out. So we will have the expression as roughly rho g s by m into CL1. Where suddenly it becomes so simple? Because remember that we have assumed CLU less than CL1, or initially I was talking about 0. The better way of handling this is you can say, okay, even if it is supersonic case, high speed case, CLU will not be 0. So I said, okay, my approximation says in any case CLU will be much less than compared to CL1, so I neglect this. So both ways you could see this, right? Second statement is better way of handling this situation. Also you know that CL1 equal to mg by Q1s, because this comes from lift equal to weight. That is our steady state. Okay. So those two information we will use. Q1s by mg is here. Okay. So if I now substitute this here, then I get omega np rho gs by m into CL1, right? And now if I further see this, we substitute this CL1 equal to mg by Q1s, then you can show that omega and Phugoid will approximately come like g by u1 root 2. Please do it yourself. You have to just substitute here. Only understanding is CLU is less compared to CL1, and CL1 is nothing but mg by half rho v square s, which is Q1s at steady state. If you substitute this, you can easily show that omega np will be approximately g by u1 root 2. So what is the message for Phugoid frequency or natural frequency omega np goes inversely with u1. So as the speed is increased, this frequency goes on decreasing. Or reverse way, if the speed is low, this Phugoid frequency is large. For gliders and all, for gliders, speed is not that high, right? This Phugoid frequency has a tendency to be little larger, and that is the fun you have. You can easily excite the Phugoid and really enjoy the Phugoid mode. Now, story doesn't end here. Now let us see zeta p, Phugoid damping, which by expression is minus xu by 2 omega np. And again I substitute the value expression for xu and all. So I will get Q1s by 2m u1 to omega np, and here I put CDU plus 2 CD1. Right. I am not taking the thrust effect. Please understand, I am not taking, I am taking CTXU identically equal to 0, and CTX1 is also not considered. Again, we will be using this concept CL1 is mg by Q1s and set it inside the expression of omega np also, and then we can easily show if I substitute this, zeta p approximately will come as CDU plus 2 CD1 by 2 CL1 root 2. What you have to do to get this expression is, you have to put omega np expression, which is here, approximate expression. You have to use CL1 equal to mg by Q1s, and then you can modify this expression zeta p equal to CDU plus 2 CD1 by 2 CL1 root 2. If zeta p equal to CDU plus 2 CD1 by 2 CL1 root 2. What next I should do as a designer to get some first hand feel? I'll immediately see CDU will be less compared to 2 CD1, number one. I can also think at subsonic speed CDU will be almost 0. The expression for damping ratio Phugoid is minus xu by 2 omega np, and we'll substitute the expression of u here, then you get the expression for zeta p as this. We are aware CL1 is mg by q1s because it has come from lift equal to weight at steady state at the cruise. So, if I substitute this, then I get expression zeta p equal to CDU plus 2 CD1 by 2 CL1 root 2, and for subsonic case, low speed case, let us say CDU can be approximately 0. So, we have now zeta p here 2 CD1 by 2 root 2 CL1, and you could see that this implies zeta p is inversely proportional to CL by CD evaluated at steady states, that is CL1 by CD1. This is extremely important. Please understand, this expression is when no thrust. We are mostly talking about the gliding flight. Okay. What is the meaning of this? If CL by CD is very large, especially for gliders, they are very large, they are order of 30s. So, that means the Phugoid damping is very, very low, right? And that is where you enjoy gliding. You excite the Phugoid, it will go on doing this long period for longer time, right? And you enjoy the flight. So, this is very, very important as far as gliding is concerned, and you should understand that as you go on increasing CL by CD, the Phugoid damping goes on reducing, right? And this is a case for no thrust case, and mostly very, very relevant for gliding flight. And we all know by flying also that gliders, we enjoy the gliding flight because we want to enjoy the Phugoid mode and enjoy this motion, right. So, this was a closer look into Phugoid approximation and short period approximation. We want to avoid using those huge metrics. We found 2 by 2 matrix we will use, and we got some relevant information in short period mode and Phugoid mode through approximations. These are very, very handy when you try to freeze initial dimension for designing an aircraft. Okay? And you will see that how we use it in our design course will be coming next. And that time you will appreciate why we are stressing so much time on this. So, this is up to the longitudinal mode. Next, now we have to go for lateral directional mode. Thank you very much.